Okay, so we've done some simulations, and now we need to actually take these simulations and look at the big picture and cover some of the big ideas. So the first big idea that we need to cover here is something we call statistical significance, and that is essentially focusing on something being considered likely or unlikely. And I guess I should really clarify that when I say unlikely, we're talking about something that happens less than 5% of the time. So if something happens 10% of the time, I guess we wouldn't really classify that as being likely, but we would call that not unlikely enough. So, the language we use in this unit is going to be kind of tricky. So first example here, Mason Jarch making a return, looking to play a dice game with you. He wants to play a game using a six-sided die and says if the outcome is a six, you pay me $5, and if the outcome is a one, I'll give you $1. You decide to play, and he rolls the die 8 times. Of those 8 rolls, 3 of them are sixes, and the other 5 are not, which means he is up $10. You accuse him of cheating by using a weighted die or an unfair die. Is your claim justified? So what we're going to do is we're going to run 100 trials of 8 rolls of a fair die to determine whether the claim is justified, whether this is something that would be considered unlikely to happen on a fair die. Okay, so again, the thing to keep in mind is that our simulation we are about to run is on a fair die. So we're going to do this using the random binomial feature. We're going to do random binomial, and we're going to do 8 rolls of a fair die, which means we have a 1/6 chance of him getting a 6. And we're going to simulate that 100 times. All right, we're going to put this into a listing spreadsheet and look at the data graphically. Now, if you don't have a calculator at home and you couldn't download the software, on OneNote, there is a list or a page that I've supplied that has the dot plots that you will need for each page. You can see that this is the dot plot that we could have used for page 4. This is the dot plot we could have used for page 7. And so I could use this dot plot here for page 8, but I'm going to go ahead and, sorry, page 10. I'm going to go ahead and still make my own. So if I go to a listing spreadsheet, so I'm going to start a new document. We're going to call the column S. You can call it anything you want. You could type out a whole word for 6 if you wanted to. It's not easy to do on a alphabetical keypad though. Then we're going to go to Menu, Data, Random, Binomial, 8 rolls of a fair die, so 1/6 chance of getting these outcomes. And we're going to simulate it 100 times. So now I'm going to add a data and statistics page and look at the data specifically for 6s. So what happened in this situation was that Mason Jarch got three 6s. And we're questioning, well, 3 out of 8 rolls, how likely is that? So you can see I've got all these dots here. And even more, 4 even happened. So the other thing you have to keep in mind with statistical significance is that you're looking at a less than 5% chance of that outcome or more extreme. So we actually have to go to find the probability of rolling greater than or equal to, sorry, that looks like a 2, greater than or equal to 3 6s. So if I go to my dot plot, I could count up the dots, or I could change it to a histogram. So if I do that, I can now hover over and see that 3 occurred 9 times, 4 occurred 2 times, and so we got 11 out of 100, right? We did 100 simulations. So it's 11 hundredths, 11%. Now, again, not that likely, but again, this is not unlikely enough to be considered statistically significant. So it is not unlikely enough that this outcome occurred on a fair die to be considered cheating, right? It's possible that this could have happened on a fair die. Okay, so we have another situation. Mason Jarch wants to win your trust back. So he modifies the game up, and he has a 6 or 1, he wins, and then everything else, you win. So now we have, if we're going to do a simulation for this one, 100 trials of 90 rolls. This time, since there's 2 outcomes that he wins with, we're going to do 2/6 or 1/3 here. And again, we're going to simulate it 100 times. It's always our go-to so that we get a nice clean decimal as our answer. So again, that you can go to the simulations for the packet, which maybe I'll do that for this one. So if we go to the page 10 example 2, you can see here's the information. And if we go back to the actual question, we're looking at the fact that 40 of them are either a 1 or a 6. So he wins 40 of the times. So we are now calculating the probability of greater than or equal to 40. We'll just say wins. This time, if I go back to that simulation, 40 is right there. And in the simulation, if I go to 40 or more extreme, we only have 2 dots. 2 dots. So now that means that the probability of greater than or equal to 40 wins was 2 out of 100, or 0.02. So now we can say it is unlikely this occurred on a fair die. And so now you can actually accuse, you have some justification to say that Mason Jarch might have cheated. Again, it's not a guarantee because it's still possible that this happens. It's just not very likely that he could have actually had this happen. So it is possible Mason Jarch cheated. Okay, so let's see what we got for the next page. All right, so now we need to look at the proportions of coin flips and proportions of outcomes. Instead of looking at the whole number, we're going to look at it as what proportion of times did we get it. So I'm going to pause, let you guys take a quick read of this. I've got the description of what to do as you kind of move along through. So if you want to pause and read and try to follow along on your own, go ahead and do so. So if you're following along with the directions here, it's going to pop up with this question of whether H is a column or a variable. So you can see how it has like the letters A, B, and C. Those are the column references. H was what we defined as a variable. So H is a variable reference. And so when we put this in, now we get all the proportions. So when we flip the coin 4 times, 1, it was 1 out of 4. 2 is 2 out of 4, or a half. 4 is 4 out of 4, which is a whole. And so I want to look at the proportions as a dot plot. And our dot plot here is always going to fall between 0 and 1 now, because they're talking more specifically about probabilities. So we're going to focus on proportions. And you can see that the x-axis scans from 0 to 1. So then it asks us to calculate the mean and the standard deviation of the proportions. So I can actually go back, and if I do a 1 variable or stack calculations, 1 variable statistical analysis, the number of lists is 1. It's always 1. and we want to focus on our proportions. So I'm going to hit P there and then hit enter. And we can see that the mean came out to be 0.485, and the standard deviation came out to be, let me scroll down for that, 0.26884. I'll round to 3 decimal places there, so I'll say 0.269. So notice the dot plot only hits values of 0, 0.25, 0.5, and 0.75. So why are the dots only occurring at the multiples of 0.25? So for an analysis on that, if we look at it, you can see that, a quarter, right? We have 1/4 of the time, if I flip a coin 4 times, 1 out of 4, then I'd get 1 out of 2, or 2 out of 4, 3 out of 4, 4 out of 4. And it's because they were for the sample size, we could say, the sample size is 4 coin flips. What we're really interested in looking at is what happens when we increase that. So now I'm going to take a look at the next page, and the next question asks us to do 8 coin flips. So I'm going to change that number in the first column and the second column to be an 8. So I'm not going to restart a new list. I'm actually just going to go back to this page, hover over this value here, and hit enter on it, and then delete the 4 and turn it into an 8, and I get new data. And now I obviously am going to have to change this to be h over 8 instead of h over 4. Again, I asked, no, it didn't ask you if it was a column or variable reference, but there you can see now, again, my answers are falling between 0 and 1. So if I go back, we had 1 coin flip that was out of 0. And actually, the nice thing too is my live data has the mean is now recalculated, 0.49375, so 0.494. The standard deviation was 0.173 or 0.174 if I round. Is the dot plot still only hitting at multiples of 0.25? And the answer to that, if I go back and look, is no. Right, we have this here occurring at an 1/8, 2/8, 3/8, 4/8, 5/8, 6/8. So the answer is no, because the sample size is now 8. So all of my answers are fractions out of 8, or decimals out of 8. So it's really the multiples of 0.125. All right, so now we're going to do the same thing and change it to 20 coin flips. So we're going to change it to a sample size of 20. So I'm going to go ahead and change this number up here to a 20. Then I'm going to change my proportion values to be out of 20, h divided by 20. And you can see that the mean is now 0.51. The standard deviation is 0.119 or 0.120 if I round to 3 decimal places. So we have 0.511, 0.120. And again, everyone's going to have something different, but there is a trend that's occurring. So this one says, why is the dot plot only hitting at multiples of 0.05? So if I go back to the dot plot now, you can see that we have 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5. And so that's because the sample size is now 20. So it's all fractions out of 20. And 1/20th is 0.05. What happens to the shape of the dot plot as the number of coin flips, the sample size, increased? So the shape, we're going to actually take a closer look at this. I'm going to piece of software I've developed that actually shows us the mean and the dot plot as I gradually increase the sample size. So right now I've got 20 coin flips presented here. And really what I want to focus on is what happens as I increase that. So right now we went from 4 to 8 to 20, but I'm going to increase it even more. So I'm going to go up to 30, then 40 and 50, and I could keep going way up to 500. And I'm hoping that we can realize that as that sample size increases to 400, 500 coin flips, it is pretty much centered right around 0.5. That it's getting clustered. So the other thing you want to pay attention to here is the standard deviation. Right? These numbers are the mean is the top number, and the S stands for the standard deviation. So as I go back down to 20, you'll see that the standard deviation is 0.163 or 0.118. And then as I increase it, that standard deviation keeps getting smaller and smaller and smaller. So the data gets more clustered. So what happens to the shape? The answer is the data gets more clustered around 0.5. And 0.5 is their, the theoretical probability of flipping a coin. What happens to the mean and standard deviation as the number of coin flips increases? Again, that's going to be the standard deviation decreases. And that's because, again, you can see it was clustering. So that kind of leads us to being able to answer some questions on the next few pages. So here you can see I have a group of dot plots, and they represent sample sizes of 20, 60, and 120. So the sample size is what's represented here. That does not mean that there's 20 dots, 60 dots, and 120 dots. So do not waste your time counting how many dots are on these dot plots. You're trying to focus on what happened. Again, we'll go back to that calculator simulation, as the sample size went from 20 to 60 to 120, right? And mine has 100 dots on it, but the ones that are here on this packet are probably only 50 if I had to guess. The other key details that's provided are the standard deviations. So pay attention to those and see if you can figure that out. All right. Okay, so I'm going to just focus on those standard deviations. The one with the largest standard deviation is dot plot 3, so that is the smallest sample size. And the one with the smallest standard deviation is dot plot 1, so that is the largest standard deviation, largest sample size. And then the middlest standard deviation would be 0.064, so that is most likely our sample size of 60. All right, so that's where I'm going to leave off on this video. It's kind of a long one. Hopefully you made it to the end. I'll write these explanations in the packet.